Okay, thank you. Good morning, everyone. When I was invited to do this, I wasn't sure what exactly to expect. But I just want to say, if you are very experienced in statistics, this is not for you. You can now start checking your emails, do whatever you need to do. I will be okay with that. This is more for the basics, okay, to discuss what we have been talking about here and make sure that we are all in the same page. So I'll try to give a few examples, maybe review a few things. Hopefully you take some good things from this lecture. Let's call a lecture. I don't know. Okay, so I created this website for where I put some classes, just to see if it opens. It has my classes. Here has some examples, programs that Charles and I created, we uploaded, but we hope some of you can use this. I have some. Those are the lectures. Let's see if I can go down here. We talk about changing pointing, autocorrelations, how to remove the annual cycles, which we do all the time, harmonic analysis, spectral analysis, filtering, principal component, and also we talk a little about wavelets, which is, I don't think is here, but so I try to create these websites to be the way we can communicate with everyone, with no exception. So, but today I will use some of this material and other things, and okay. I recommend also, if you are interested in statistics, Wilks should be your Bible. So Wilks is the Bible for statistical analysis. It's a very good and friendly book. I also like Chatfield is a good book. And Rodrigo Bombardi had this idea of publishing a paper in which he wants to discuss the practical problems that we have in climatology, and this is in Portuguese. So you can also, everyone can have access to this as well. So we all have this problem. We have too much data, right? We need what to do with things we have. And we may understand the problem. Sometimes we do not understand. We have no clues about what to expect, and we need to find answers. Other times, we do know where we want to go, but how to get there. And we have this big 3D, everything very complex, and what to do with them. So the problem is everything is in space, but also in time, right? So every one of those elements in this figure can be seen as a time series, and so we want to know how to deal with this time series. So we know that by definition that a time series is a collection of observations in time. It can be discrete, which usually the case, right? If you have a model, you have or reanalysis, you have every day, daily, or you have hourly. So this is discrete. And you can have continuous, let's say, obtained by on all temporal scales, say by an instrument, which is not always the case, but now you have to deal with the processes. What are the processes that explain the sequence of events that I'm looking at? How do I deal with these processes? I may know how the process was constructed, and I can say, okay, this is a deterministic process. So I know the equations generated that result. Now, when you say deterministic, we may know the equations, but doesn't mean that necessarily it is a deterministic, that I know the solution, because sometimes deterministic equations can diverge, and then you can have chaos, and then you have all sorts of problems we call deterministic chaos. And if you want to read more about what I'm talking about, I like this paper. It's an old paper, but they explain very well what chaos is and how we can, what chaos means in deterministic approaches. So the other thing we talk a lot about is what is a stochastic process. The word stochastics come from Greek. That means the hidden rules. So you know about learn about the future of events or hidden rules by means or know based on reason. What do they mean? We use this word to say, okay, we know nothing, but we are going to understand these processes through some sort of what we call a stochastic approach, which means finding hidden rules using probabilistic approach, using statistics. This is most what we have seen here, our discussions here were based on the idea that we have stochastic processes explaining our time series. So some examples, we asked these questions throughout this workshop. Say what drives the monsoon variability. We don't know the equations that could explain that, but we use stochastic processes to or see this data as a stochastic process to understand these questions. What modulates convection, how the Atlantic or the Pacific modulate the monsoon, and so on. So we take our data sets, can be multiple data sets, to find out the hidden rules. So how we can describe our time series if we don't know the deterministic, what generated the time series? We can represent a time series as simply, let's say, some trend, some seasonal cycle, and something else, okay? So a trend, it may exist or not. We can even say, okay, a trend is a deterministic part. If I assume it's a linear trend, I know about the trend, I can say this is the deterministic part. Say I can approach this for a linear regression and find out this trend. The other part is the seasonal cycle. I'll talk a little later about the seasonal cycle. And then this is the part that usually is the most interesting. That's the part we'd like to find out about, right? And everything else we are actually trying to investigate. So first, let's say we have your data sets and you are interested in everything else, the epsilon component. So what you can do first, you can fit a linear trend in your data sets if you suspect it's linear, and then you can remove this linear trend. Now what you have left is basically your epsilon can be described by this new data set minus this part, which is the seasonal cycle. Let's see how we can represent this seasonal cycle. Usually, if you have this problem, what do you do? You would take, let's say you have daily data, and then you will be calculating your daily averages, right? And if you do that, and I challenge you to do, if you haven't done, take any time series you're looking at and start calculating the annual cycle just by calculating averages. In this case, I'm assuming this is daily data, okay? So you calculate even if you have 20 years, 40 years of reanalysis, whatever you are analyzing, if you calculate, you're going to see that you're going to find after you calculate that your average is actually this. Ups and downs, ups and downs, ups and downs, okay? A very common problem, and this is what made Rodrigo be a little upset sometimes, that people start using this as the annual cycle. But there is a problem when you use this as your annual cycle. Here, I took this from this paper. He's showing the annual cycle calculated. Here, in dashed line is if you filter past a moving average. And this is another fit using harmonics. I will talk about harmonics soon. So if you end up using, this is just showing, if you assume that the annual cycle is this line here, and if you just subtract, remove the annual cycle, you may find your anomalies. It's just an example of the anomalies. We still see some the anomalies also have a seasonality. It's very common we see that in our data sets because anomalies can have also seasonality. And this is very common to observe. Anomalies are near zero, but you still see some seasonality. Now, if you remove the cycle without filtering, you are actually adding perturbations, random perturbations to your anomalies. This can be larger if you have a less, your seasonal cycles are not based on too many years, and yet can be important because if you are interpreting now your anomalies, and maybe if you add noise, then you are interpreting noise, right? So filtering your annual cycle is very important so you avoid interpreting noise because you may not find what you are looking for, right? So basically, this is the idea. Now, we also are interested, it's not only the annual cycle. We talk here about the decadal variability, the multi-decadal variability, the seasonal, intraseasonal, synoptic variability. So it's all there. It's all embedded in your data sets. And we want to also to understand those oscillations, those variabilities. And then comes the idea of Fourier, which I think he one of these greatest insights was to understand that all signals, all time series, doesn't matter which time series we are talking about, can be decomposed into harmonics. And I will show you what I mean by that. I'll give you an example. Now, you have two things are important for understanding harmonics is that each harmonic has a period, is a wave, is an oscillation that has a period or a frequency, and also is associated with a wave number. I'll give an example. Maybe this will be clear. So this is my time series, original time series. And you see, as I advance, here you're going to see the wave number. Here you're going to see the period of the wave and how I will reconstruct the original time series by adding harmonics to this time series. I will start here. Just a second. Start. Okay, so this side, you are going to see the harmonics. I will go back so you understand a little better. So every time K advances, I'm not putting all Ks, but some Ks, you're going to see the wave, how I represent the wave, and the amplitude of the wave is also shown as I advance. I will play again just to show, just so what to look at in this. So again, I start with K equal to 1, K equal to 2 is a long period. K equal to 24 is actually the annual cycle. K equal to 200 and 400. You see that they're very tiny. The amplitude is very tiny. But at the same time, they are contributing to go back to the original time series. So the original time series is a contribution of all those harmonics that are summed with different amplitudes. The largest amplitude in this case is the annual cycle. You can clearly see when you look at the right side. You see that this is the annual cycle, the most important, but all other cycles are embedded in this time series. Okay. Now, how we describe this with these ideas of harmonics? Harmonics can be described as functions, trigonometric functions, simple as cosines and sines. And the trigonometric functions are also interesting because they can repeat. If we keep going, adding more and more angles, this will be repeating over and over and over and over. It's bounded by limits, -1, +1, right? You can repeat it. And also interesting is that they have a difference in phase. This is very important. Sine is 90-degree difference in phase relative to cosines. So you can use these functions to represent oscillations in your time series, and then that was the idea of Fourier. But we have a problem, as I just said. If you are using sines and cosines, well, they are bounded between 1 and -1. And our time series go from whatever to whatever, right? So we need to do something to adjust for that, which is adjusting for the amplitude, the actual amplitude of the data. Also need to understand that, well, not always your first dates or is a cosine, like the maximum is in the beginning or the minimum in the middle. So you have to adjust for the phase of the waves, okay? So those are the two problems we have usually when you're dealing with a Fourier analysis. And then you have softwares today, and we provide some programs if you are interested, how to calculate this, these functions and these amplitudes. But ultimately, what you want to do is to represent your series like this, okay? All your time series that your unknown can be represented like this. This is your observation at time t. Any observation can be represented by the mean value that you take from all your observations. You take all of them and calculate the mean. But at a single point, you have the mean plus the contribution of all other harmonics that is represented by the cosine. Here, the argument of the cosine is the frequency, which depends on k and t, okay? And n is simply the number of data points you have. So every single point in your time series can be reconstructed if you calculate all these ck's, which are the amplitude, and you know also the phase of that harmonic. But you can calculate all that based on your data. That's the beauty, right? You take your data, you use your data to calculate all these amplitudes, the phase of your harmonics, and you can play with that as you wish. What do you need that? Well, you can use this to say, I want to isolate some of these frequencies I'm interested in analyzing, and I can take that and filter from the rest. I can use this to reconstruct some part of the series, or I can calculate, even use these ideas to calculate the spectrum, to know which one of these frequencies is more important in my data set. Calculation of the phases can be complicated, but because cosines and sines have different phases, you can represent the same equation instead of a phase. You can decompose into cosine and sine, right? And then you have two coefficients. They will tell you which one, the sine or the cosine, is more important at that time t. And then with that simple, beautiful, in my view, representation, you can reconstruct all these oscillations in your series and study them as well. The amplitude, then, in this case, is given by the root square of these two, AK, BK squared. That gives you the amplitude. Now, amplitudes. We've been talking about intraseasonal, interannual, decadal, multidecadal. If we assume this is true, we want to study this. We have to prove that these are important contributions in our time series. They are above the background of what to say red noise. They are above that. They make sense because you may try to study intraseasonal variability in a place where there is no intraseasonal variability. Intraseasonal variability is as important as any other variability. So you start doing this, you start getting nowhere because you're trying to see, I want to see if this makes sense to me, but I'm having the wrong problem. I'm having the wrong hypothesis that I can actually see intraseasonal variability. If my time series, this doesn't matter. Okay? So it's always important. I want to mention that is a lot about the construction. If n is the number of data points, keep in mind that you have the maximum number of harmonics to reconstruct the entire time series, n divided by 2. Just to recollect that k equal 1 is one cycle. In the entire time series, you have one cycle, one maximum, one minimum. K equal 2 is 2 cycles in the entire time series. K equal 3 cycles, and so on and so forth, okay? I give another example. This is also from the paper, just show this figure. In this case, we can reconstruct this annual cycle. Instead of using moving average, we can fit the first harmonics. Of course, the first one that shows one cycle in the entire 365 days is the most important. But you can start adding more and more just to get closer to the actual annual cycle. In this case, Rodrigo reconstructed this with 3 harmonics. Do we need these 3 harmonics? Very unlikely. But if you are doing your program and you don't know, you are doing this approach and you're not going to look at 1 million time series in your data set, you can just assume as an algorithm, as a code in our program, that you're going to use the first 3 harmonics to reconstruct your annual cycle. And this should be good enough, right? Okay. So this is a recommendation, just a rule of thumb. You can calculate annual cycle if you are interested in using this type of approach. You first calculate your annual cycle like this, and then you may want to filter the annual cycle, or you can fit the first 2 to 3 harmonics to your annual cycle, and you should get this dotted line here after you do this approach, okay? And more details you can find in the website. There are also complicated annual cycles. This is also taken from the book of Wilkes. And he's showing just a calculation here, the relative frequency of days with 0 precipitation. This is not precipitation itself, but it's a different analysis. He has this time series, and you can see this is kind of different. It's 360 days. You see a peak here, peak there, a bottom here. And let's say you are assuming, well, annual cycles are always looking alike, but not always the case. So in this case, which cycle has the highest amplitude? K equal 1 or 2? You have 2 peaks here. Which one? K equal 2, right? So the second harmonic is more important than the first harmonic. So assuming that the first harmonic is always the most important for the annual cycles may not be true in all cases. So be careful. It's always good to use more than one harmonic to fit your annual cycles, right? Why do you also want that approach? As I was saying before, we want to know if your time series have some type of important forcing. What is forcing your time series to be, in this case, I'll give you an example of winds. We were studying winds in these two regions, in the Amazon and northern near Pará, and this is Rondônia. And this is OLR, outgoing long wave radiation, and zonal winds in both places. And we did that. Our scientific question was, is there any subseasonal variability in these winds? What is the peak of the subseasonal variability, if it does exist? Meaning that, are these winds forced by some type of waves, or the MJO, or synoptic timescales, or easterly waves, or any kind of oscillation that is on these timescales? That was our question. And so we calculated the spectrum. The spectrum is based on Fourier analysis. And what matters in our interpretation is always to interpret what is above a certain level of significance. So there's a lot of behind constructing this. I'm not here to tell you how to construct this, but we have a very good recipe in our website that Charles created that you can go step by step and learn how to do your spectral analysis, okay? I'm not going to talk about this. It's just the importance of using this. In this particular case, we show that OLR in Rondônia actually has a peak near 36 days and also 21 days. North of Pará. Rondônia is kind of shorter timescales and longer timescales in this area, which is consistent with what we have seen in these discussions during this monsoon workshop. The other method we have been talking a lot about here is principal component analysis. We use this all the time, and we read this in papers all the time. We heard Alice and everybody else talk about principal components, and I want to make sure that we are on the same page. We understand what this is. Because principal component is the most used and popular approach. Sometimes it's very common when people don't know what to find out about the data, they take the anomalies and say, oh, let me run a principal component analysis and see what I find out. Sometimes it's a good idea, other times makes you even more confused. Another thing that's important is that principal component and empirical orthogonal functions means the same thing, right? Lawrence, 1956, he coined this name empirical orthogonal functions because he realized that if you take different portions of your time series, you may not find the same results. So this is an interesting point. That's why empirical came. Sometimes we say factor analysis, but Wilkes says don't do that. Okay. What's the idea behind PCAs? In principle, was to reduce the number of possibilities on your data to make it simpler, right? You have a lot of data and you don't know what to do with that. We want to make sense of all this information. And PCAs are designed to help you to do this. As long as this type of PCA, as long as there are linear relationships. There are no linear PCAs, but in this case, we are thinking of linear relationships. Another desired objective is to find the main patterns of variability that explain your data set. You have your data of winds and you don't know, say, what explains. Can I find explanations, patterns that, spatial patterns that are important, temporal as well? So I can use PCAs. Sometimes I don't know about the patterns, other times I know about the patterns. I'll give some examples. So in other words, you have a lot of data, multiple objects randomly packed together, and you want to select the good ones, the ones that will be more important in explaining what is inside all this trash, and then you want to make a garbage that makes sense for you, okay? And then you can interpret how this varies over time, and so on. So I'll give you a very simple example I always give in my class, and to show how this works. It's a very silly, stupid, of course, no one is going to use a principal component if you have two variables, right? You want a 2 reduced to 1. Big deal, right? So, but I want to show this because it's a 2D visual explanation that may help you to understand more multidimensional problem. So here, imagine you have 2 stations with temperature in 2 different locations, and then you'd like to simplify the problem. Actually, you want to find how to reduce this to one information only. Okay. First thing first, we take an average. The average of these 2 stations is around 10 Celsius, have only 15 observations. It is a stupid problem, right? It's just to illustrate this, okay? So first, we should all do, we plot our data, right? So you plot station 1 against station 2, and you find this nicely linear regression or linear plot here, right? This is good. Then you may ask yourself, okay, I want to find an equation that explains the behavior of station 2 based on station 1, or station 1 based on station 2. So you see that when I do this, I have 2 different equations. So finding the common behavior using regression actually is a complicated problem because you end up having 2 types of equations. And we don't know exactly how to use and in this case. So what you'd like to do is to obtain a single equation, a single line, put this way, that can represent the entire behavior of your data set. And minimize the deviation or maximize the explanation of the variance. I want to explain most of this variability of my data set. Okay. So first thing that is behind calculating PC analysis is to calculate the covariance matrix. So in other words, when you do this, when you are calculating your PC analysis, you want to know how different grid points talk to each other, how correlated they are. Because they may be correlated close to you, but they may also be correlated far from you. So you want to know these relationships. And this is, in a linear approach, very easily explained in a covariance matrix. You could think of correlation matrix, but in this case, I'm showing the covariance matrix. So the covariance matrix in the diagonal shows the variance of the data, and across the diagonal, the covariance of the data. So this is what, this is just a calculation based on that data set. I'm showing this variance being here, the covariance matrix. Now, what is PC? Now it's going to be a big jump I have all in detail in my classes. I hope, if you're interested, you can see the mathematical approach in more detail. But basically, finding a principal component is an eigenvector, eigenvalue problem, right? And everything we want to do is to find this U, which is a matrix of eigenvectors that if I calculate the transpose, multiply by the covariance matrix, and again by this vector, I end up with this diagonal matrix of eigenvalues. Very complicated problem, but it's linear algebra, basically. So we call these eigenvalues, they have an importance. And you see that the importance is that if I sum all these eigenvalues, I will end up having, well, it's not shown here, but it's the sum of the total variance of the data. If I sum all these eigenvalues, will be the total variance, entire variance of the entire data set. Okay. So in a PC analysis, the total number, what's the total number of PCs I could find in my data set is always equal to the number of time series you are analyzing, or the number of data you are analyzing. So in our silly problem, this number is equal to 2. I have only 2 possible eigenvectors and eigenvalues to represent this data set. If I had 100 points, 100 grid points, I would have 100 possible principal components. Let's analyze those two principal components. First of all, again, I repeat, this is a silly problem. So when you find the first eigenvalue using that mathematical approach, you see that the first eigenvalue is showing in pink. It is actually very close to the regression line. And this is, notice that most of the variance of the data, so minimizes the variance. The distance between the data points and this vector is minimum. Now, you see that it rotates relative to the original axis. This is the original axis of your data that originates the plots. Now, if you calculate this angle here, this is the angle between station 2 and the eigenvector. And this is the angle of the station, the station 1. That's the orientation of station 1 and the eigenvector. And this is the angle between the orientation of station 2 and the eigenvector. Now, if you calculate these angles, it's easily shown here. And you calculate the cosines of these angles. The cosine is actually the components of your eigenvector. In other words, you are seeing another projection. You found this orientation explains maximum variance, and now you're finding how your data set projects in that particular direction. So this is actually showing a projection, and these coefficients will be used to interpret then your data sets. We can, based on this, there is a second component. The second component is always perpendicular. The idea is going to be there is no projections between U2 and U1. They have zero projection. They are perpendicular. And I can find also what is the new projections of the axis onto this U2 eigenvector. I can calculate the same way, and these two coefficients will be the coefficient of my second eigenvector. Okay. The other important thing now is that I have my data sets, and I can reproject my observations in these two eigenvectors. And then I will interpret this over time. And now, the way I do this, I call this the first PC, the second PC, and then I can recalculate this projection over time. Instead of having the original value, I will have a projection of these values onto these two axes. And there's an equation that we can use, and we call this temporal coefficient, time coefficient. Some people even say PC as a simplification. But this is always the projection onto this axis. So if we interpret these two behaviors here, you see that the behavior 1 is actually, PC1 is just telling you variables go along together. When it's hot in one location, it's hot in the other location. When it's cold in one location, it's cold in the other location. This is what this PC1 is telling you. And PC2 is the opposite. Sometimes it's not as cold in one location. It's not as hot. It's near zero. So it shows some behavior that is not explained by this linear relationship. I'll give a quick example. Let's take this observation over there, calculate the projection on first EOF. It's equal to this value. Now let's calculate the projection on the second EOF. It's very tiny. It's equal to minus 0.009, a little negative. Now let's see the other observation over here. Projection on the first EOF is actually negative because it's below the mean, it's negative. And in the second EOF is positive and almost at the same magnitude. How do I interpret this? Now comes my interpretation. How do I interpret this problem? First case, you have PC1 greater than PC2. I can say that day both stations were behaving the same way. Both have positive anomalies. In the second case, I have these two combined information. I can say this other day, station 1 was near me, station 2 was below me, not very typical PC1 behavior. Too bad for your forecast, okay? Didn't behave as you expected because it's far from your PC1, and you rely on your PC1, and you think that, well, that day it failed, okay? Now, we can imagine, let's extrapolate this stupid problem for a more real one. Now you have anomalies. Let's say you want to find an index for ENSO. That was one problem we talk a lot about here. How would you do? Well, first you select your area of interest. It's very important. Take your time series long enough, as long as you can. Look at the anomalies. Always important to have the anomalies. The means need to be extracted. Maybe the annual cycles need to be extracted as well. And then you interpret each one of these grid points as a time series and do what I showed, but now you have a multiple dimensional problem with several eigenvectors to interpret. Okay, and so you see that if you do this, your first eigenvector will be the ENSO. So this is just an explanation. You can also then, the same way, look at the time coefficients. And the time coefficients of this EOF will tell you how your ENSO varied. And you can use that as your, instead of looking at all the anomalies over the Pacific, you can just look at your time coefficient, your index. Here is, I took this from a paper of Dye, and I forgot to put the name. Oh no, Dye and Wigley, 2000. And this is what they found. This is the first EOF of the sea surface anomalies. And this is just, he took this one of these, the black is the time coefficient. Let's put this way to simplify. It's not exactly, but, and then he's using this to interpret situations of El Niño and La Niña. How did he does that? He takes the time coefficient and says, okay, now I'm going to analyze years where this index is above 1, where it's below 1, and now I can do my composites. That's how we use this. I calculate, I find the time coefficient, and I do composites based on this time coefficient. Now he did here, he used a typical El Niño, so he took all cases, all years that were above some level, I believe it was 1, and did the composites for precipitation. He found this. Oh, fine, you have your thesis, you have your paper. Simple as that. Now, this is one I took from Alice's work. What she did here, you can explain better, but what she did here, you have precipitation, right? This is precipitation. Yeah. This is precipitation, and she calculated the EOFs, and she interpreting the first mode, the first EOF, and what you see here is the time coefficient. What you see here is the pattern. So the pattern now is projected in space. In my problem, I just had one line, one information. But here, for every grid point, now you know how each grid point is talking to each other in the first EOF. So only one direction. We are looking one EOF, one single direction. There are many. The number of data points here is the number of PCs she found, but she interpreting only the first one. And the time coefficient, she can use this to isolate the problem as she wish. There is also a second mode, right? I said it has the same number of EOFs that the number of data points she has in this analysis, and the second EOF is showing something different. So as I said before, like the orthogonal line is showing a behavior that has nothing to do with the first one, same story here. It's supposed to be independent. It's supposed to be orthogonal. That's why it makes sense to interpret, because you have two different behaviors. We have to test for independence. It's not as simple as it is, but you know, this is just to show the idea. And then you can do your research using these processes. I've talked about using multiple variables. You can do that as well. Same idea. Instead of having one time series, you take one time series of several different variables. Now you're making it more and more complex. It requires memory, of course, depending on the number of variables you have. And then you calculate the covariance matrix. Same story. And then you will end up having. I'm talking about Lisan again. You can use, in this case, I used to calculate the index for the monsoon, and I use variables that are related to the monsoon: circulation, precipitation, moisture, temperature. And I use for this not entire domain, the domain was a little smaller. And then those were the variables that I used. And then I used, we call now, because it's a multiple, we call combined empirical orthogonal functions in this case. And in the same way, I interpret the first two modes. And now I'm showing, again, as I showed for Alice, 5 minutes. I showed, now I have, in the case of Alice's result, she had a projection for precipitation because that was the only data set she was using. Now I have a projection for all data sets that will project and tell me about what I was looking for. I was looking to see the precipitation. I want to point out that we also have negatives and positives, and then they are telling you how the covariance, how data is covariant among itself. The second EOF was the SACZ, so I interpret as something perpendicular, which is very interesting because everybody thinks that SACZ is always related to the monsoon, but over the ocean, it's very independent. It appears as an independent EOF as an independent phenomena that is not necessarily linked to what is happening over the continent. And this is an important thing we have been using to study monsoon in South America. Okay, and now again, I interpret these different signals, and that's why I know that this is the convergence zone as well, because it has a signal in precipitation and temperature and everything. That also goes to what Marcelo was talking about. We are discussing related to temperatures, what the relationship between the SACZ and temperature, air temperature, not ocean temperature, over the ocean. Okay, this is how the time coefficients looks like. So you have the first. Keep in mind as you analyze EOFs that are EOFs are also related to frequency, right? The first EOF tends to be more low frequency, then you start adding higher frequencies. And so EOFs can be also a filter, can be sometimes used as a filter. So we have this, we use this for the monsoon, as I explained before, to talk about the onset and demise. We can use this for the monsoon. We also use this to, we calculate the amplitude based on this EOFs. You calculate the integral, we assume to be an amplitude. But what I was going to show is that the time coefficient also has some information on the frequencies that dominate the signal. So if you remove the annual cycle from the listen index, you end up, if you remove the annual cycle and you take the upper quartile and lower quartile of this index, you end up actually isolating the wets and active and break phases of the monsoon. That's why I was saying that its signal is similar to what you showed yesterday. So you have westerlies, and you have also a strong signal near central eastern Brazil. Okay. So here's showing just a spectral analysis. So you see that the index does have a power spectrum on subseasonal time scales. We can also, you see that we assume that every EOF is orthogonal, but we can also relax this idea. You can find EOFs that try to find eigenvectors that explain more the variance, relaxing the idea of orthogonality. This we call rotated EOFs. Very important. I also remind you that interpretation of EOFs is important based on tests of significance, and this is the paper we have been using, the idea to test the significance of the EOFs. Just showing some of the rotated EOFs that Alice showed before, but I think I need to take question. Okay. See that. Probably use much more than that time.
I think you captured the intention.
Okay, thank you.
Okay, so let's see the first question.
And nowadays we use the PCA to define some indexes to some patterns. Like, for example, in Southern Annular mode, we use this and say, okay, in this year we have a positive sum, and in the other year we have a negative. But it is possible to use this to forecast the signal of some pattern.
You can, well, the way you would do is you have your forecast, and you can project your forecasting, what you're saying, like creating a statistical forecast?
No, for example, in the operational, we need to know if in the next 3 months we have a positive sum or
Okay.
ENSO.
Okay,
But
okay.
ENSO is easy because we
okay.
calculated the SST anomaly.
Yeah.
But the sum, normally we use the EOF to define
Yeah,
this,
you can.
this pattern.
What's normally done, you have your forecast, your data sets, right? Run your models, and then you can use this EOF and see what is the how your forecast projects into these EOFs, okay? How strong is the projection? You have your data, and then you can project and say, okay, is projecting strongly, is showing that the projection is high, and then you can say, okay, the mode is there and is strong, right? Make sense?
Very nice class. I already shared your webpage with my students. In the last spectrum that you showed for South America, you mentioned intraseasonal peak. So there is no interannual peak important here, or what happened?
No, this is actually, we did this for seasonal, so I didn't explain this well. So during the rainy season, so what we do is this is a ensemble spectral only during the rainy season. So we don't have the interannual because we are only have 4 or 5 months. You see, so we are not going to capture this. If you want to look at the interannual, then you cannot do this. You need to take the entire time series and then capture all types of variabilities you want. In this case, we just want to look into during the summer. There's an ensemble me. All right.
Thank you for your lecture. It was very nice. I enjoyed very much. And normally the first and second and up to third AOF give the highest variance, explain variance, and we can explain that patterns.
Right.
But then from maybe fourth, fifth, and so on, they have a lower explained variability, but maybe they have some meaning that maybe some patterns we can't understand, but maybe they have some
meaning.
hiding features that maybe we could explore more. What do you think about this?
Well, I tend to be very careful about this because, first of all, this is the method we always try to find the number of eigenvectors equal to the number of data points. So some of this, the method by definition does that. It's not factor analysis. We are not rotating, so we have to this constraint, right? And this is just maybe spurious results because there is a tendency in finding maybe that particular days or year, things didn't behave, so it orients a vector, but not necessarily has a meaning. So it's always an issue what to decide about the number of EOFs that makes sense to interpret. I usually use the North-et-al rule, because we guarantee that they are independent. Because sometimes you find EOFs, but it's the same story. They're telling you the same story, just the opposite sign. So these things help you to decide. I wouldn't interpret noise, right? Or things that they don't actually make much sense if you have a much bigger data set, they may not even appear important. That's my philosophy.
Well, thank you for your presentation. It's always nice to have a good review, you know, of the basic concepts. Have you some experience on irregular time-spaced time series and applying those methods?
No. But you can. No, yes, of course, yes. No, yes. You mean like you don't have a equally spaced time? No, yeah. It doesn't matter. You can do this with the data you have. It doesn't require to have equally spaced observations. No, it's not prerequisite.
Okay, I just would add one step further for people. Now that Iracema asked her question, I remembered it because she asked something about hidden mechanism or something related to the mechanisms of these EOFs. Well, when you calculate these EOFs, actually the first one has, by construction, to accumulate the most variance it can, regardless of the mechanisms underlying the mode. So then, for instance, you have this dipole mode over South America, as I showed for this intraseasonal variability. You have this big region to the north, the dipole, the center of the dipole to the north was a big region. But actually this big region with these anomalies are not produced by the same mechanism. But by construction, you have to put all the factor loadings that happen there in this region in the same mode. Mm-hmm. But then there is another resource you can use, and you know it, of course, it's the rotation of modes. Mm-hmm. And this helps sorting out similar mechanisms. So it regionalizes better the modes. Then this first mode of intraseasonal variability was divided into two rotated modes. One with the northern center of the dipole more to the north, in southern part of northeast Brazil, and the other over the South Atlantic convergence zone. The northern part was due to tropics teleconnections. Kelvin waves and eastward propagating Rossby waves. Whereas the southern part over the Sax was due to extratropics teleconnections. But they happen in the same period of these on average, 6 days of phase one, with a very little lag between them. So when you rotate them, there is also this question of the degeneracy of the modes. When you have non-rotated modes, you can use this criterion she mentioned of North et al. But this criterion doesn't apply on rotated modes. Mm-hmm. Actually, when you rotate, you already avoid this problem of degeneracy. And also you avoid, at least most, the problem of the effect of the domain on the modes. So rotating the modes help to avoid several of these drawbacks of the EOF analysis.
Yeah, unrotated modes usually show lots of dipoles, tripoles, and then we start rotating because you do that by retaining fewer EOFs, and then you redistribute the variance onto these fewer EOFs, and then you tend to eliminate all these dipoles. It's something to keep in mind because things can be different if you do one way or another.
Okay, concerning Iracema question, I think that there is another a single solution. If you are interested on higher frequency modes, and you can filter the data in that scale that you are interested on, then do the
Absolutely.
EOF, then the mode that you are looking for would appear in the first or second mode.
That's very true. That's one. First, do your spectral analysis. Don't do these things without making sure you're not analyzing noise. Makes sense? Then you can do what she's saying, filter your data and recalculate your EOFs. That's a better way of studying the low frequency sometime or high frequency, whatever.
Yeah, it's better to filter than you concentrate on a certain time, a frequency band more specifically. But even so, it's good to rotate them, because even if you have this unrotated mode for a specific frequency band, you still can have these problems of the unrotated mode. But a very good suggestion, yes, to already separate frequency bands. Okay. So,
You
thank
done?
you very much
Thank you.
for your... Okay, well, now, do you think we should do this discussion now or after the lunch, or... 15 para uma. I think something we will... Huh? Na discussão agora ou depois? So, just